Let's say that we have a rather large list of stocks, and you need to perform some calculation on each of them. They have nothing to do with each other, and the calculation can be done independently. To simulate a little bit of load, I'm going to introduce a method that simply spins a loop for a few seconds before it's returning a value back to the caller. If you call this method on a thread, that thread will be busy running the loop for the given time. If we call this method on multiple different threads, which is the goal, that would consume 100% of the CPU available on the system until that operation completes. This will ensure that the problem is solved as quickly as possible. Our computers are most definitely different and have different CPUs. We're going to write code that effectively distributes work across all the available resources. No matter if I run the code or if you run the code, we can be sure that it will run as effectively as possible on each system. If we call this method, it will produce a result as a stock calculation. This just contains some fake information for us to populate the application with. It will also contain the amount of time it took to perform the operation. This application provides some fake stock data, which we're going to process. I've already added an in-memory collection of data to make it a little bit more interesting. The data will generate random amount of stock prices and some data inside of it. Exactly the contents of this isn't really the important part. What we are going to focus on is speeding up the application. These are all completely independent from each other. Therefore, we could assume that the processing can be done completely separately. Each stock identifier presents a chunk of stock prices. In our example, it's just some generated prices. We can process these chunks in parallel, which will speed up the process of analyzing them. Roughly, if I have 12 available cores, I could process 12 of these at the same time. That's including processing one on the UI thread. These operations are CPU-bound, and that's the perfect fit for parallel programming. If, however, most of the time were spent waiting for the operating system to return file contents or a result from a web invocation, that would be an asynchronous process. And then using the asynchronous principles would be more appropriate. Before we introduce the parallel principles, let's first add the code in a non-parallel manner to see how it will later improve the experience of the application. I'm going to compute the result for each of the different stock identifiers to simulate a little bit of load. Once all the different stocks have been processed, we'll add the result to the UI. Running this and invoking the search button will run our piece of test code. Don't worry about searching for an actual stock. That code hasn't been added. You'll notice that it takes a fair bit of time to process each of the stocks. It will also lock the UI until all of them have completed processing. This is, of course, because we're doing all of the work on the UI, or the main thread of the application. Your first urge to solve this is maybe to introduce a task.run and wrap all the heavy code in a new task. However, the problem with that approach is that you'll only move the work to one additional thread. You will then have one thread that takes care of the UI and one thread that processes the work. The user experience will be improved, but the process of the operation isn't really faster. Since all of the calls to the method calculate are completely independent, wouldn't it be great if they were all processed in parallel? And certainly that's the goal. You could run each of them in a separate task.run, but you'd end up writing a lot more code than you have to in order to, for instance, handle each continuation. Instead, we're going to use the parallel class. This introduces a few helpers that will allow us to more easily approach this. Internally, it will in fact use the task from the task parallel library. It will also provide some configuration capabilities to override some behavior. Out of the box, it will take care of calculating the most efficient way of dividing the tasks it's given among the available cores. This means distributing the work effectively across the different cores that you have available on your system. If we simply spawn a lot of tasks using task.run, not only will it not be as efficient as it could be, it will also require us to write a lot more code than we have to. Instead of doing that, we can use the methods available on the Parallel class. We could use Parallel for, which is really the same as a normal for loop, but it will run in parallel and be configured to distribute the work according to the system it's running on. You could also use the Parallel for each, which is a parallel version of the normal for each loop. These two will be covered later. You've also got a method called invoke on the Parallel class. This takes a list of actions. These actions will be distributed and executed in parallel. None of the methods on the Parallel class will guarantee that it's executing in parallel, because it really depends on the system. I've had a look at the internals of Parallel invoke, and depending on how many actions you pass to it, it might execute them using a parallel for loop. This just proves that it does some really heavy lifting and provides some great functionality and optimizations, which you shouldn't take lightly. Parallel invoke doesn't return anything, and the actions you pass to it are distributed to run as effectively as possible and run independent from each other.